Thank you very much, Anna. So the title of my talk is Impact-Based Surface Treatment for Enhanced Fatigue Performance in Additive Manufactured Parts. This is the work that has been done with by our past PhD student, and for Maleki, myself, Dr. Bandini from Pin Service in Italy, and Professor Mario Guagliano. So as we are working with laser powder bed fusion technology, we know that there are many different types of defects, bulk defects like pores, lack of fusion, tensile residual stresses, and anisotropic microstructural characteristics. But at the same time, we have a lot of surface defects. So it's a big problem at the moment for all different additive manufacturing technologies, because we normally have, not normally, we always, I would say, have very regular surface morphology. In the case of laser powder bed fusion, we have the partially melted powder or unmelted powders that are agglomerated randomly on the top surface of the part. So they are causing a lot of issues for many wide range of applications, including wear, corrosion, fatigue. Even for aesthetic point of view, this is not, let's say, the best solution in terms of surface morphology that we can get. Apart from the technology parameters, also the geometry and the shape are affecting the surface morphology, as we are having some variation in the angle of, let's say, surface with respect to the build direction. We see a lot of irregularities and variation in the distribution of local surface softness in laser powder bed fusion. Here, for example, you can see a notched part that has very different surface features in the down-facing area with respect to the notch root and the up-facing area. Here you can see different, let's say, technologies, optical microscope or micro CT or a scanning electron microscope images that we took in order to show how inhomogeneous the surface softness is as we are changing the build direction with respect to the surfaces of the part. So in order to enhance and homogenize the microstructure, there are different methodologies that are suggested in the literature as post-processing surface treatment for additive manufactured parts. We have grouped them into subtractive, non-subtractive, and then coating technologies. The focus of our research is mostly on some of these non-subtractive techniques, which are inducing severe plastic deformation on the surface in order to, let's say, flatten a little bit the surface softness, and combining them with some of the subtractive techniques. So overall, we are performing also a bulk post-treatment, which is a heat treatment. And then we are considering many different surface treatments, including the subtractive one. Chemical polishing and electrochemical polishing. We are considering another group of technologies that are based on severe plastic deformation, especially, let's say, shot peening, which is an impact-based surface treatment in which small particles are accelerated with compressed gas in order to impact the surface and induce plastic deformation. Then we have used also surface ultrasonic nanocrystalline surface modification technique that in concept is very similar to shot peening, because we are always having, let's say, the impact on the surface, but the impact is being applied by a tungsten carbide ball that is being pressed to the surface and is moving into a specific route. And then we have considered also severe vibratory peening that is, again, very similar to shot peening, but in this case, we have a limited number of shots that are enclosed inside the chamber and are accelerated in order to impact the surface of the part. And lastly, we have considered also laser shock peening. So we are considering, let's say, the individual effect of each of these parameters, these treatments, and also the combined effect together with this chemical or electrochemical polishing in order to see how much they would affect the mechanical response of our samples. Starting from the heat treatment, so we see that the clear inhomogeneous microstructure in the as-built condition that is becoming much more homogeneous after heat treatment. So the laser traces are being faded, and there is a slight grain coarsening, but in general, the microstructure is becoming much more homogeneous after the heat treatment. And here you can see the surface morphology, the top surface morphology of our samples after different surface treatments, starting from the very, let's say, inhomogeneous and random surface softness in as built condition, and then shot pinning with the typical, let's say, dimples that are caused by the plastic deformation induced by each single particle. Then the results for UNSM, SVP, CP, and ECP, which are the electrochemical and chemical polishing, which are the giving us the, let's say, the smoothest surfaces, because they are removing, let's say, the top surface layer slightly and giving us much smoother surface. We have done these treatments all on the as-built condition and also on the heat-treated samples. And here you can see the quantification of the roughness parameters. In most cases, we are reducing the surface roughness, and we are decreasing also slightly the scatter with respect to the as-built condition. We have characterized the samples also in terms of micro-hardness, porosity, and residual stresses. As expected, all the treatments that are based on plastic deformation on enhancing the surface micro-hardness, or let's say micro-hardness of a layer close to the surface. They are slightly reducing the porosity because they are closing the pores that are very close to the surface. So the subsurface pores are being closed because of the plastic deformation that is induced on the top surface layer. And we have compared also the depth of the layer that is related to the closure of the pores with respect to the surface. And you can see all the treatments are introducing pore closure, but to different extent with respect to the mechanism that is being involved there. And we are inducing compressive residual stresses with all these treatments. So again, to different extent in terms of surface residual stress, the depth of the layer that is affected by compressive residual stresses, and the maximum value of the residual stresses. On the other hand, the treatments, the chemical and electrochemical treatments, are not interfering with these parameters. So they are mainly reducing the surface softness, but not inducing, obviously, any residual stresses or changing the micro hardness. And finally, we performed rotating bending fatigue test at a fixed stress level on these samples in order to compare the fatigue life that we could get from each of these treatments. Here you can see that all of the treatments are, you see the as-built sample that has a very poor performance. And then after the heat treatment, we are already improving the fatigue performance because we are homogenizing the microstructure and releasing the tensile residual stresses. But then with the other treatment, as we are changing the surface softness and inducing also compressive residual stresses, we are considerably increasing the fatigue performance of the part with this treatment, and especially the hybrid treatments where we are combining the severe plastic deformation based technique with followed by a electrochemical or chemical polishing. We are getting the best results because we are getting all the benefits from the residual stresses and the surface, let's say, parameters, hardness, and that is changed. But we are also removing the top surface layer, which has the highest surface roughness. So we are reducing also the surface roughness in that area. One interesting observation was that we normally would expect the failure to happen at the notch root, but in all these samples, let's say in the especially in the as-built sample, we always had the fracture section on the down-facing area where we had the highest surface roughness in our samples. As we are applying these treatments, we were able to displace the fracture section to the let's say critical notch root. And here, as we quantified, let's say this distance, you can see that the hybrid treatments were able to bring the fracture surface to the critical area. Focusing on shot pinning, which was the main impact-based treatment that we considered, we tried also to develop a new treatment, as we called it, gradient shot pinning. What we do normally in shot pinning is that we fix a pressure that is inducing, let's say, the kinetic energy that is being transmitted to the material, and then we would change the exposure time. With this treatment, we were increasing the as-built samples roughness. Although the fatigue performance was improved, but we always had the issue with the roughness. So with this gradient shot pinning, what we did is that we are continuously changing the pressure during the process. With different strategies, we considered, let's say, this ascending severe shot pinning. We are always at the very high, let's say, Allman intensities, but we are starting from intermediate Allman intensity and going up to a high one. Another strategy was ascending, descending severe shot pinning. So we are starting from a let's say, almond intensity that is being used by conventional treatments, going to much higher almond intensity, and then coming back to the original value. And in this way, we wanted to kind of modulate the surface softness as we are performing the process of shot pinning. The results here were very interesting because with the ascending, descending shot pinning, especially, we were able to reduce considerably the surface softness with respect to the other, let's say, treatments, while maintaining the compressive residual stresses and all the other positive effects of the shot pinning treatment. And here you can see the results in terms of rotating bending fatigue test, that the best results again were obtained with the ascending descending shot pinning, which was getting the highest, let's say, the good compressive residual stresses, and at the same time reducing the surface softness. To conclude, we tried many different post-processing treatments in order to enhance the performance of additive manufactured parts, in order to control mainly the surface layer properties. Of course, the treatments that are based on severe plastic deformation can have pore closure effect. They reduce the surface softness or homogenize, let's say, at least the surface softness, depending on the treatment. And they are also inducing compressive residual stresses, while the ones that are based on chemical surface treatments are just not interfering, let's say, with the bulk material, but just changing the surface morphology. But there's no unique solution to say which treatment is the best for additive manufacturing, depending on the geometry of the parts that we are going to treat. We have some limitations in terms of the practical limitation of using which treatment, depending on the size, depending on the type of the material. So it's a matter of finding, let's say, the best solution, depending on a case-by-case study, which one would be the best. But the combination of the treatments seems to give us the best results in terms of fatigue performance of additive manufactured parts. Thank you very much for your attention. I would be happy to answer.
Thank you, Sara, for this fantastic talk. Are there questions from your side? Yes.
Thank you for a very nice presentation. I have one question about the parameters of shot pinning. It's possible to vary by these parameters of shot pinning in your instruments? Because in conventional material is well known that exists some optimizing or optimal pre-straining level, which increase the fatigue limit. When it's smaller or higher, decrease. That if you have possibility to vary by these parameters and to find some optimum of these shot pinning parameters.
Sure. And so for, as you mentioned, for conventional shot pinning, you would have a range of, let's say, a limited range of parameters that would give you the best results in terms of fatigue performance. That is, we call it conventional shot pinning. And then if we increase a little bit, not a little bit, sometimes even double the almond intensity, or keep the same almond intensity or slightly increase it, and at the same time increase the exposure time, we get to a treatment that we call it severe shot pinning, that is inducing also surface nanocrystallization. So it's true that we are maybe inducing some surface defects, but at the same time, we are nanocrystallizing the surface layer and inducing deeper and higher values of compressive residual stresses. So there's a, let's say, a compromise between different parameters. And sometimes with severe shot pinning, in many cases, we've been able to increase even further the fatigue performance despite the high surface softness. With gradient shot pinning, we are kind of moving between these two limits. So starting from conventional to severe, and then with different strategies, moving between these two limits. And that has helped us to enhance the surface quality in terms of roughness.
Any other question? Mark? Yes. Don't.
Thank you, Sara, for your nice presentation. My question is about the effect of shot pinning in moving the crack initiation site below or on the surface. So did you have any information regarding this?
It's a tricky question because we are, let's say, competing between some surface defects and then the compressive residual stresses. I can say in the case of ascending, descending, which was, let's say, our winner solution, in most cases, we had subsurface crack initiation. So although we had, let's say, some surface defects, but overall, we had lower surface roughness with respect to severe shot peening, and we had quite deep compressive residual stresses. So that in most cases helped us to displace the initiation point from the surface to the subsurface area.
In your opinion, is this superficial crack initiation site located where compressive residual stresses are no longer present?
To be honest, we haven't got much deep in that area, but I suppose in conventional shot peening, my observation has been like that. So it's mostly where residual stresses, compressive residual stresses are fading or relaxing, or let's say, it depends very much on the depth of the layer that has been affected by compressive residual stress. Specifically on these samples, we have not, let's say, quantified this, but based on my experience with conventional shot peening, I would say that has definitely an important effect.
Thank you.